what is backpropagation ultimately? Backpropagation is nothing but, as we've seen in the semantics of backpropagation for, say, linear or sigmoid activation function, you always take the differential of the activation function and look at the delta and compute the resultant delta W to update the delta W of the previous layer, which is what is the typical mechanism of what is known as gradient descent, which is basically moving through the direction of maximum descent and updating the previous layer's W. So here, when we have multiple unfolded loops for, say, a loop which has, say, 4 loops. So the original state is unfolded to S1, S2, S3, S4. Ideally, you would have the output of E3, S3 would be based on differential with respect to the first weight of S0. But here, if you see, it is as good as take the differential of error at 3 with S3, then multiply it with delta of S3 with S2, and delta of S2 with S1, delta of S1 with S0. And if you look at the computation of delta with respect to W, which is the W at E0, it will be as good as chain rule multiplication of delta of E3 by whatever is the delta at Y3, then delta of Y3 as at S3, then delta of S3 divided by delta of W. And if you look at each point, the error propagates by chain rule to the next previous layer, next previous layer, next previous layer, etc. So this is what we call as backpropagation through time. And it is as good as applying the conventional gradient descent rule over T cycles, and then ultimately giving the final output at the end of the T loops, which is what we're going to pass on to the previous layer. So this is all fine, well and good. It's able to perform the same function like a multi-layer perceptron. But here is the catch. The catch is very simple. The catch is, in all of these cases, we have multiple iterations over the same slope, T loops. Now, let us take a simple example of when you take a delta and multiply it over and over again multiple times, what happens to the actual delta? Let us say at the first layer, the delta was 0.99. Now, suppose we have loops which are, say, 10 loops. So what happens that next layer you have to multiply 0.99 with again something less than 0.99. Again, you have to multiply that with again something which is less than 0.99. Like that, you have 0.99 expressed power n number of times, t number of times. T may be very large. So what happens is the net output at one T loop is a very small number as compared to what the original error was. So let me repeat. Anything which is less than 1, which is as a typically delta, once you put it over T times to the power, it becomes a very small number. Let's take a very small idea. Let's take 0.5 as the error. 0.5 square becomes 0.25. 0.25 square becomes 0.0625. And then 0.0625 square maybe becomes 0.003 something. So you can see in number of T loops, the delta tends to become a very, very small number. And that is a mathematical curse for applying RNNs, though the elegance of the loops enables us to carry forward memory and allows us to model sequential problems, etc. But it leads to the problem, which is what we call as vanishing gradients, which is basically means, as I said, if the gradient is 0.5 or 0.9, and as we speak of applying it over t loops, it really tends to 0. And imagine what happens is if each weight gets added delta w, where delta w is close to 0, imagine what's going to happen. What's going to happen is deltas will be always 0 and there'll be hardly any change to the weights, and it's possible that your neural network will not converge and weights will remain stagnant at some point where from where it's not changing any further. And that is one of the biggest loophole of RNNs, which is what we call as a vanishing gradients, which is compounded by two things: typical delta being less than 0, and backpropagation through time requires us to take the delta and multiply several times over smaller values than delta, which is going to ultimately lead you to a very small delta, which may not be able to give any meaningful memory, and it may lead to not converging neural networks. So gradient vanishing is a huge problem in applying RNNs as is. So it may be very good for very short-term dependencies, maybe just immediate past word or something. But the moment you go into anything which is a slightly long-range dependence, like earlier part of a sentence, then vanishing gradient issue is not able to confer upon RNN the capability of long-term memory, because the gradients are not able to update the weights significantly when they are much smaller in volume, less than 1, and when they are multiplied in number of times. Let's say, for example, I have to ask the RNN to complete the sentence: I grew up in France, I speak fluent dash. So here it is basically referring to a word which is four words much before the current word. This is a long-term dependency. So remembering long-term context is not possible in RNNs because of the vanishing gradients problem. And it is because of this precise problem of vanishing gradients that we have alternate architectures to the RNN architectures, which is very important from the perspective of understanding why and where these are useful. So as I said, in the scenario above, RNNs were not strong enough to predict the word French because they don't work with long dependencies and hence cannot read the long-term context. That's where LSTMs and some of the newer RNN variants have been brought into the picture to be able to give neural networks the power to model and work with sequential data, give it a strong formalism, and yet be able to carry out a long-term prediction. Because otherwise, without long-term prediction, sequential models will not be able to work because we don't know what part of the previous data it is able to use for prediction. It cannot be always a very, very near term, which is probably what RNNs may be primarily geared towards.